Good morning all. In this video lecture we will discuss about NMR spectroscopy. So it's a nuclear magnetic resonance spectroscopy, most commonly known as NMR spectroscopy or magnetic resonance spectroscopy. It is a spectroscopic technique to observe local magnetic fields around atomic nuclei. So as you all very well aware that protons and neutrons in a nucleus behave as if they are spinning. And if the total number of neutrons and protons is an odd number, the atoms will have a net nuclear spin. For example, 1H, 13C, 15F, 15N, 19F and 31P. The spinning charge in the nucleus creates a magnetic moment. So these nuclei can be thought of as tiny magnets. So as you all know that when a bar magnet, like in this picture you could see here the bar magnet, like a bar magnet, a magnetic moment exists perpendicular to the axis of the nuclear spin. If the normally disordered magnetic moments of atoms are exposed to an external magnetic field, their magnetic moments will align. So in this picture you can see here this is magnetic moment showing in the absence of the magnetic field. So in the applied magnetic field, these magnetic moments will try to align itself with or against the field. And this slide represents the aligned magnetic moments can be either with or against the external magnetic field. So the magnetic moments, if it is aligned with the applied magnetic field, that is being represented as alpha. Against the magnetic moment which is aligned against the external magnetic field is represented as beta. And this is the energy level. Please have a look at this diagram. This is the alpha spin state and this is the beta spin state. And the difference between these two spin states is being represented as del E, that is the difference in the energy level. So when an atom with an alpha spin state, so let's assume when an atom with an alpha spin state is exposed to radio waves of just the right energy, it can be promoted to beta spin state. So stronger the magnetic field, the greater the energy gap can be. And it's very clearly understood in this picture. And this picture shows the magnetic moment of electrons generally reduces the effect of the applied external field. The more shielded a nucleus is with the electron density, the smaller the alpha. So you can see here in this diagram represents the circulation of electrons around the proton. So shielding is there here, shielding is there. So the amount of radio wave energy which is necessary for the transition from alpha state to beta state depends on the electronic environment for the atom, either it is shielded or deshielded. But when the alpha spins are flipped to beta spins, the atoms are said to be in resonance. Okay, so how will you acquire the NMR spectrum? So the NMR spectrum requires a strong magnetic field and the radio wave energy, and the strength of the magnetic field affects the energy gap. Just have a look at this diagram. This diagram represents the energy level del E, difference in energy level del E. So for one kind of atom, it requires for the magnetic field strength is 1.41 beta test, 1.41 Tesla, wherein uh, wherein there is a transition of electron from alpha spin state to beta spin state. Similarly, for this setup, It is B naught is equal to 7.04 Tesla. It requires for it to transit from alpha to spin state. It means that for it to to be in reson to be in resonance, the required amount of field is 7.04 Tesla over here. When a strong magnetic field is created, when a high current is passed through a superconducting material at extremely low temperature, this could happen. And the greater the current, the greater the magnetic field. And in most current NMR instruments, a brief pulse of radio energy is used to excite the sample. Each of the atoms is excited and then relaxes, emitting energy. The emitted energy is recorded as a free induction decay. So this FID contains all of the information for each atom. A mathematical treatment called the Fourier transform separates the signals so an individual signal can be observed for each atom that was excited. Such instrument is called as FT-NMR. Often multiple FIDs are taken and averaged together. So before analysis, this NMR samples must be prepared in a, prepared neat or in a liquid solution and is placed in a small NMR tube. The sample is placed into the magnetic field and the tube is spun at a high rate to average magnetic field variations or for tube imperfections. And this is the diagram which represents the NMR spectrometer. And you could see here this is the superconducting magnet, and this magnet is cooled by the liquid helium, where this supplies the magnetic fields. And you have a sample tube which spins with the probe coils in the hollow bore at the center of the magnet. You have the sample tube here. Whatever the radio frequency generator RF signals is being a short wave of RF pulse is passed to this, as we have seen how the NMR signals are produced. So the RF generator and this is a computer console which shows the RF the RF detector, the received RF signal, and the received signal, the Fourier transformation of the signal will be done over here. And you could see here this is the RF excitation pulse, and resulting NMR signals are sent through the cables between the probe coils in the magnet and the computer. And the magnet is always supercooled, but the sample generally at a room temperature. The sample will be at a room temperature only. So you will get the resulting NMR signal. The resulting NMR signal will be like this. The way this graph represents the NMR signal, and this NMR spectra contains a lot of structural information. One is the number of signals and the signal location or a shift from the reference, that we call this as a chemical shift, and the signal area and the signal shape. So this is how NMR signals are acquired and used for analysis. Hope you have understood this video lecture. Thanks for watching.